Alright, welcome back. This week we're going to do Chapter 3 out of the Cosmic Perspective book on the science of astronomy. Here's a picture of astronaut John Grunsfeld, who worked on the Hubble Space Telescope. He is in the front cover of your textbook and now leads up the astronomy division for the National Science Foundation. So our goals for this section, the ancient roots of science, are going to be in what ways do humans use scientific thinking, and how is modern science rooted in ancient astronomy. So what ways do humans use scientific thinking? Well, we look at scientific thinking and it's based on everyday ideas of observation and trial and error experiments. So how is the science of everything related to ancient astronomy? Well, we know that many of our current systems had their roots in the achievements of ancient astronomy. This includes timekeeping of the day, tracking the seasons with the stars, the calendars, monitoring lunar cycles, monitoring planets and stars, and predicting eclipses, and much more. So the ancient people of Central Africa, and this is looking at 8,500 years ago, could predict the seasons from the orientation of a crescent moon. They knew that in the summertime they got more rainfall than they did in the wintertime, which was their dry season. So the days of the week were named for the sun, moon, and the visible planets. And so you see here on this graph, which is in your book, Sunday was named after the sun, Monday named after the moon, Tuesday named after the Germanic god of Mars, Wednesday was named for Mercury, Thursday was named for the Germanic god of Jupiter named Thor, Friday was Freya of Venus, and Saturday was named after Saturn. Well, here is a huge Egyptian obelisk, and the shadows of this object tell us the time of day. And so a lot of the ancient sundials use this same procedure. Then we have Stonehenge out in England. This was completed around 1550 before Christ. So how does Stonehenge work? Well, it shows that archaeologists believe that Stonehenge looked upon its completion in 1550 BC. Several astronomical alignments are shown as they appear from the center. For example, the sun rises directly over the heel stone on the summer solstice. And so we believe this to be an ancient astronomical timekeeper and calendar. There's also a model of a Temple Mayor in Mexico that was also doing the same thing. And in New Mexico, the Indians did the same thing, ancient Aztecs. In the southwestern United States, there is a sun dagger on a rock formation that marks the summer solstice. And in Scotland, there's a 4,000-year-old stone circle. The moon rises as shown here every 18.6 years. And another one here in Peru, the lines and patterns, some of them are aligned with the stars. And Machu Picchu in Peru, structures aligned with the solstices. In the South Pacific, the Polynesians were very skilled in the art of celestial navigation. In France, cave paintings from 18,000 years ago, 20,000 years ago, may suggest knowledge of lunar phases with the 29 dots. In China, the earliest known records of supernova explosions go back to 1400 BC. We know they saw one of these in that time period. So what has this section taught us? In what ways do all humans use scientific thinking? We know that we use scientific thinking. It involves the same type of trial and error thinking that we use in our everyday life, but in a carefully organized way. It's modern science rooted in ancient astronomy because many of our modern timekeeping systems have ancient roots. So let's take a look now at the ancient Greek science. And we're talking thousands of years ago when the Greeks were more of a philosopher than anything. So our goals for this section, 3.2, is why does modern science trace its roots to the Greeks? And how did the Greeks explain planetary motion? We'll look at that. So we know back in those times there was a humongous library of Alexandria. And this is a reconstruction drawing of that library. The Greeks were the first people known to make models of nature, and remember from the first lecture that a model is just a simplified version of something complex in nature. So they tried to explain the patterns in nature without resorting to myth or the supernatural. And so back 400 BC, we're talking 2,500 years ago, the Greeks had what was called a geocentric model, and this was basically the model that the Earth was in the center of everything. Since we live on the Earth, why not have the Earth be the center of the solar system and the center of the universe and everything that goes around it? Makes sense, right? Well, there's a special little demonstration here. You can read this for yourself in the book. But basically, Aristotle measured the Earth in 240 BC. And so what he did, he looked at wells dug into the ground at both two locations, Syene and Alexandria. The distance was 5,000 stadia, which was kind of the distance used back in that time, kind of like kilometers or miles. And the angle difference was 7 degrees, 360. And so he was able to convert this distance to be the size of the Earth of 42,000 kilometers. Not bad for 2,400 years ago. So how did the Greeks explain the planetary motion? Well, the basic understanding of the Greek geocentric, geo meaning earth-centered, was that the Earth was at the center of the universe and the heavens must be perfect. Objects moving on perfect spheres or in perfect circles. Now these perfect circles were at one time called God paths because the Greeks believed that if there was a God, that God made the universe perfect, made the Earth perfect, made everything in the universe perfect, and we live on the Earth, which is made perfect. So we call these orbits, we call them nowadays, or these spheres, perfect circles, God paths. But this made it difficult to explain apparent retrograde motion of planets, which we talked about in week 2. This is where the Earth overtakes the orbit of Mars, and for a brief few months, Mars appears to go backwards in the sky. And so over a period of 10 weeks, Mars appears to stop, back up, and then go forward again as we pass it, just like we did on the highway last week. Well, the most sophisticated of all the different Greek models was the Ptolemaic model. The P there is silent, Ptolemaic. This is 100 or 170 AD after death. It was sufficiently accurate to remain in use for a very long time, 1,500 years. And so the Arabic translation of Ptolemy's work was named the Almagest, the greatest compilation. And Ptolemy was a philosopher. So how does the Ptolemaic motion explain this retrograde motion that we have seen in the sky at this time? In Ptolemy's model, the planets actually went backwards. And so what we had was this great big circle that went around the Earth, that the planet went around, and then the planet itself went around in little bitty small circles around the big circle in this model. And we call these epicycles. So here we have the Earth, we have an orbit around the Earth, but then in the orbit around the Earth there's a little bitty sphere going in a smaller circle, and that would account for the backwards motion. So how is the Greek knowledge preserved throughout history? We know that the Muslim world preserved and enhanced the knowledge they received from the Greeks. Word spread pretty quickly. There was a house of wisdom in Baghdad that was a great center of learning around 800 AD. And with the fall of Constantinople In Istanbul in 1453, the Eastern scholars headed west to Europe, carrying knowledge that helped ignite the European Renaissance. So we trace modern science roots to the Greeks. They developed models of nature and emphasized that with predictions of models, they should agree with observations. And so the Greeks explained the planetary motion, especially the backwards motion, with a Ptolemaic model that each planet moved on a small circle whose center moved around Earth in a bigger circle. Always keep this in mind. The best explanation is usually the simplest. So does this model seem simple to you? A large circle going around the Earth and then smaller circles going around that circle. Doesn't seem very simple to me. So here we come to a big time in astronomy. This is section 3.3, the Copernican Revolution. So we're going to talk about Nicholas Copernicus here and what he did in the 1500s. So our goals for learning this chapter is going to be how did Copernicus, Tycho Brahe, and Johannes Kepler challenge the Earth-centered model. What are Kepler's 3 laws of planetary motion? And how did Galileo solidify the Copernican Revolution? So we'll take a look at these folks, these men that were very, very instrumental in where we are today with modern astronomy. And to avoid the confusion, some of these guys go by last names like Copernicus and Kepler. Some of them went by their first names, Tycho Brahe and Galileo Galilei. So here's Copernicus. That's from 1473 to 1543. And what he did was he proposed a sun-centered model. Call this heliocentric. Helios meaning sun. This was published in 1543. It used a model to determine the layout of the solar system, planetary distances. In that term we used the first week, astronomical units. That's the average distance from the Earth to the Sun, 93 million miles, 150 million kilometers. But there's a problem. The model was no more accurate than the old Greek model, the Ptolemaic model, in predicting the planetary positions because it still used these perfect circles, the God paths. So here comes along a cool guy. This is Tycho Brahe, and I'll tell you a story about this that you will not find in your book and you will not hear anywhere else. It's been passed down to me through many years. So Tycho was not he was an astronomer, not a physicist, not a mathematician. Tycho was very, very good for his day and time, 1546 to 1600s. He was a very good observational astronomer. He could tell the positions of planets very accurately. And so he compiled the most accurate naked eye measurements ever made of planetary motions to that point. He still could not detect stellar parallax and thus still thought Earth must be at the center of the solar system. But he did recognize that the other planets did go around the sun. Now, Tycho, being an astronomer, he needed help with the math and the physics. So he hired Johannes Kepler. Now, Kepler used Tycho's observations to discover the truth about planetary motion. Alright, so here comes the crazy story about Tycho and Kepler. Tycho was an astronomer. He was the royal Danish astronomer to the King of Denmark. And he was invited to dinner one day. Now, Tycho had his own little observatory on a little bitty island in the middle of a lake out there. So the king invited Tycho to dinner one night. The tradition, as the story goes, is that you don't finish your meal and get up from the table until the king is done with their meal. And the king at that time had a lot of meat on the bones, and he would eat a lot and enjoyed a nice cold refreshing beverage from time to time. So the king was eating and drinking happily, and Tycho was doing the same, but Tycho had to use the men's room. King was not done with his dinner yet, and Tycho sat there and started to sweat and get anxious, and all of a sudden Tycho's bladder exploded, and he died a couple days later of infection. So guess what Kepler did? Kepler took all of his 40 years of observations and he stole them. He took him away. He worked for Tycho, so he's the boss now, and he took him away and took control of those observations. So here he is, Johannes Kepler, 1571 to 1630. Kepler first tried to match Tycho's observations with circular orbits. This is what we've thought now for 2,000 years. But there was a discrepancy that led him eventually to believe the orbits were eclipses. And Kepler once said, "If I had believed that we could ignore these 8 minutes of arc, this slight difference, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore this evidence, those 8 minutes pointed the road to a completely reformation in astronomy." And what he did was he changed the circular orbits to ellipses, ovals. So what is an ellipse? Here you see it. And the best way we have to make an ellipse is you take 2 thumbtacks and put them in a corkboard. Take a piece of string and wrap it around those 2 thumbtacks, and then take a pencil and you'll draw out an ellipse. Now we'll try to get away from some of the geometry technical details of an ellipse, but basically one of the most important things is where you put those 2 thumbtacks to make the ellipse. Those are called focus points or foci. If the 2 points are right in the middle, then that's a perfect circle. But in this case they're not. They're separated by a distance, and so you get an oval. One of Kepler's laws is that the Sun actually occupies a focal point in an ellipse of the orbit. At the other ellipse, there's nothing. So we're going to talk about Kepler's 3 laws of planetary motion. This is extremely critical information that you must learn and know and understand. Let me say that again. This is critical. Kepler's 3 laws of planetary motion. So the first law, and most laws come in threes, and one of them is an equation usually. So here's Kepler's first law. The orbit of each planet around the Sun is an ellipse, not a circle, with the Sun at one focus. And so here we see the Sun right here at a focal point. And then the planets go around that in an oval. Kepler's second law is what I call the equal areas and equal time law. Let's say we're looking at a month, and a planet sweeps around the Sun very close to it in a month's time, and we see this chunk of the orbit. Think of this as a piece of pizza. Here's a pizza slice right here, and this perihelion means closest point to the Sun. Over here on the other side, during a month, it goes to a smaller chunk of pizza, but actually the areas of both chunks of pizza are the same. Hence the equal area and equal time law. What this really means is that when it's close to the Sun, when the planet is close to the Sun at perihelion, it has to go faster than when it's at aphelion, away from the Sun, it has to go slower to make this happen. But the areas of both chunks are the same. Here is Kepler's third law, and I'll tell you right now, I'm not a real big fan of equations and math in a class like this. I know our lab has a bunch of math in it, and I'm going to work with you on that to curve that a little bit to adjust for everybody's differences in math ability. But this is one of those equations you just absolutely have to know to use and learn. This is Kepler's third law, and it says the more distant planets orbit the Sun at slower average speeds. So here we have p squared equals a cubed. P is the orbital period of the planet in years. It must be in years. A is the average distance from the Sun in astronomical units. So you need to understand this is probably the most important equation, and it's simple to understand. P squared equals a cubed. You can do it on a calculator. How did Galileo come to play with this? Galileo came along a little bit later on, 1564 to 1642. Lived a long life. Galileo is often said to have invented the telescope. That is actually not true. Some Italian lens makers actually invented the telescope. Galileo was the first to actually use this new device to look into the heavens. So what Galileo did was he compared and overcame major objections to the Copernican view. 3 key objections rooted in the Aristotle view were this. Number 1, Earth could not be moving because objects in air would be left behind. 2, a non-circular orbit could not be perfect, as the heavens should be. And 3, if Earth was really orbiting the Sun, we would detect stellar parallax. Now, keep in mind, during this time in Europe, the church was really in charge of things. And the church kind of dictated how science and philosophers believed. And so for Galileo now to come out and say, you know, these orbits are not perfect. They don't follow a God path. They are ellipses. This upset some people in the church. So, the nature of motion, the first objection, Galileo's experiments showed that objects in air would stay with the Earth as it moves. Aristotle, however, thought that all objects naturally come to rest. Galileo showed that objects will stay in motion unless a force acts to slow them down. And this is Newton's first law of motion. We'll discuss his other laws of motion as well. Again, one's an equation and they come in threes. So, object at rest will stay at rest, and object in motion will stay in motion unless acted upon by an outside force. That's Newton's first law of motion. The second objection of heavenly perfection, these God paths, and everything had to be in a nice little circle. Tycho, the astronomer, his observations of comets and supernovas, stars that massively explode, already challenged this idea. With Galileo's new telescope, he saw that there were sunspots on the sun, meaning it was imperfect. He also found mountains and valleys on the moon, proving that it was not a perfect sphere. So since these things are not perfect, this upset the church a lot. The third objection was parallax. Remember we did that thumb thing where you close one eye and you move the other eye and your thumb appears to move apparently? So Tycho thought he had measured stellar parallaxes, but a lack of parallax seemed to rule out an orbiting Earth. Galileo actually showed stars must be much further away than Tycho originally thought, in part by using his telescope to see the Milky Way and its countless individual stars. So if the stars were much farther away, then a lack of detectable parallax was no longer a troubling issue. So this is actually Galileo's drawings. He looked at the moons of Jupiter. We didn't know there were moons of Jupiter until Galileo got his telescope out in 1609-1610. Galileo saw 4 moons orbiting Jupiter, also proving that not all objects orbit the Earth, which again led to an imperfection. So this is his actual drawings of these moons around Jupiter, and you can see by the day how they change. Galileo also showed with his observations that the phases of Venus proved that it orbited the Sun and not the Earth, because Venus does exhibit phases like the Moon does because it's closer to the Sun than we are. And so in a Ptolemaic world this would not happen, but he found it did happen. So here's what happened. The Catholic Church ordered Galileo to recant his claim that Earth orbits the Sun in 1633. They were not happy with him, and he was put under house arrest for the rest of his life. Thankfully, his teachings went all across Europe pretty quickly. He wrote a book on the subject, and that book was removed from the Church's Index of Banned Books in 1824. Later on, in the 20th century, Pope John Paul II came out and actually did a 13-year-long investigation of Galileo, and finally, under Pope John Paul II in 1992, Galileo was formally vindicated by the Church. Now, what really happened was the Pope came out and said, you know, this Galileo guy, he was probably right the whole time, but we're not going to apologize for putting him under house arrest. But, I mean, we probably made a mistake in doing that, and he probably was certainly right. So what have we learned in this section? How did Copernicus, Tycho, and Kepler change the Earth-centered idea? Copernicus created a sun-centered model. Tycho Brahe provided the data needed to improve this model, and Johannes Kepler found a model that fit his data. The Kepler's 3 laws of planetary motion, again, very, very, very critical you learn these 3 laws. Law number 1, the orbit of the planets is an ellipse, not a circle, with the sun at one focus. Law 2, as a planet moves around its orbit, it sweeps out equal areas in equal time. And the 3rd law is that more distant planets orbit the sun at a slower average speed. So Jupiter and Saturn go around the sun slower than the Earth and Mars and Venus does. And this is the p squared equals a cubed law. What was Galileo's role in this? His experiments and observations overcame the remaining objections to the sun-centered solar system model. Almost done here. Let's take a look at the nature of science itself. Our goals here are: how can we distinguish science from non-science? What is astronomy and what is astrology? And what is a scientific theory? So these are the ways we can distinguish science from non-science or fiction. We decide that science can be surprisingly difficult. Science, the word, comes from the Latin scientia, meaning knowledge. But not all knowledge comes from science. So we have developed, and this is true for any science class, and I'm sure some of you have already had a science class where you learned this. This is how we decide how a science works. So we first want to make observations. And then we ask ourselves a question about those observations. And once we do that, we can suggest a hypothesis. A hypothesis is nothing more than an educated guess. It's a first guess, but it's got some basis to it. With that guess, we can make a prediction of how things are going to work. And then we actually do an experiment. We perform a test, and the experiment either works or it does not work, and we have to go back to a new educated guess, a new hypothesis. Science rarely proceeds in this ideal way, though, however. For example, sometimes we start by just looking and then coming up with possible explanations. Sometimes we follow our intuition rather than a particular line of evidence. So this is called a scientific model. And one of the things about science, some people are asking about science and faith and how do those interact. Well, we know that modern science seeks to explain observed phenomena that rely solely on natural causes. And so a scientific model cannot include a divine intervention. Number 2, science progresses through the creation and the testing of models of nature that explain the observations as simply as possible. And this is what's called Occam's razor. Simplicity. The simpler model is probably your best model. Don't get too complicated like the guys in the Greeks did. Number 3, a scientific model must make testable predictions about natural phenomena that would focus us to revise or abandon the model if the predictions do not agree with observations. So if it works out, great. If it don't, we have to throw it away, try again with a new hypothesis, a new educated guess. So we've heard about theories and laws. One instance is the Big Bang Theory, a good guess as to how the universe was started. And then you also know about the law of gravity. So let's say what a theory is and what a law is. The word theory has a different meaning in science than in everyday life. In science, a theory is not the same as a guess, a hypothesis. What it really is that a scientific theory must explain a wide variety of observations with a few simple principles and must be supported by a large, compelling body of evidence. It must not have failed any crucial or critical test in its validity. So how can we distinguish science from non-science? Science seeks to explain stuff that relies solely on natural causes, progresses through the creation and testing of models of nature, and the models must make testable predictions. A theory is a model that explains a wide variety of observations in terms of a few general principles that have survived repeated over and over, and a variety of ways of testing it. Here's a little fun part about astrology. We hear about astronomy and astrology, different signs, where's my sun at, where's my moon at, what does it all mean, why are they similar but different? And of course a lot of students say, oh, you're an astrologer. No, I'm an astronomer. Astrologers are those guys down the corner with a little shop with a neon sign that charges you $20 to look at your crystal ball. So how is astrology different from astronomy, and does astrology have any scientific validity? One common joke we have, someone says to the first day of class, what's the difference between astronomy and astrology? And we say, lots and lots of math. And it's kind of true. So how is astrology different from astronomy, the science? Astronomy is a science focused on learning about stars, planets, and other celestial objects and how they work. Astrology is a search for hidden influences on human lives based on the positions of planets and stars in the sky. So does this have any validity in science? Does astrology have? The scientific tests have shown that astrological predictions are no more accurate than we should expect from pure chance alone. So astronomy is a scientific study of the universe and the celestial objects within it. Astrology, however, assumes that the positions of celestial objects influence human events. How does astrology have any scientific validity? Scientific tests have shown that the predictions of astrology are no more accurate than pure chance.